Good afternoon, 6 hour. This video is to hopefully help you with the notes for today. So, another person who described the motion of particle as wave is Edwin Schrodinger, and he mostly focused on the pattern and the movement of electrons. Just basically know that electrons move and they sometimes make a wave pattern as they move through space, because they're very light. The wave is going to be bigger than, say, the wave of an atom, and obviously it'll be bigger than like my wave at the microscopic level. Once again, with his equation, we were able to do some more calculation, pretty complicated stuff that we're not going to worry about, like in the upper right hand corner. But it did tell you that every little second, the electron will jump around to a different spot around the nucleus. And the area that it most likely going to be in, aka as you can see is the darker pattern over here, is going to be the atomic orbital. So this is where most likely the first level of electrons will be basically ground state number 1 for, say, a hydrogen atom. So every dot is a probability of where the electron will most likely going to be. So right now it's 9:30 at night on Thursday night. I'm most likely going to be at home. Not guarantee. I can be out eating a sandwich or something at Cup Food or somewhere else, but I'm most likely going to be at home. So my atomic orbital, aka my home, is the most likely going to find me at 9 o'clock at night. So different level or orbital exists in an atom, because there's obviously not just one electron in some atom. So some of the bigger atom will have electron at multiple energy level, and even if it's a smaller atom, it can have electron go from level 1 to level 3 or level 5 even, and fall back down. That energy level, once again, is indicated by the principal quantum number, the letter n. And the bigger the n number, the higher it is off or farther away from the nucleus, therefore it takes more energy to get up there. So bigger volume, bigger space, more energy. So N3 will be way bigger than N1, more energy than N1. Now within every level, like pretending the building, like an upside down pyramid, there'll be sub energy level. So level 1 only has one type of room. Level 2 will have 2 type of room. Level 3 can have 3. Level 4 can have 4. Not room numbers, but type or category of rooms, aka orbital. So I'm going to use word room along with word orbital to make it easier for you to understand. And again, an orbital is a place where an electron most likely going to be at. So as I'm doing this, I'm in my office, not in the living room. So there are 4 main type of orbital that you need to know. We're going to call them SPDF. S is simply a spherical shape in 3 dimensions, like a layer, like a basketball surrounding the air on the inside. P will be the 3 axes, X, Y, and Z, pointing up, down, left, right, and in, out in 3 dimensions. And D will be the 4 additional diagonal space that go from left, right to, going from upper right down to the lower left diagonally, and then vice versa. So slicing something as a sheet this way, and then also in and out, which is hard for you to imagine. But I'll show you in person again with my hand, maybe on Monday. You need to know the shape of SPD. S, sphere. P is called the dumbbell shape or the infinity shape. And D looks like a 4-leaf clover because it covers the 4 diagonal spaces in between the X, Y, and Z axis. And there's one additional D that covers the Z axis with a donut shape in the middle. But that one you don't need to recognize. As long as you can recognize the clover shape as D, you should be okay. And then these are just example of the F that fits in between the spaces of the D and the P. I'm not going to ask you to recognize this because there are different lobes, shape and size to maximize the spacing between the negative electron. Because remember, electrons are negative, they repel each other. So this orbital gives them the most comfortable space for them to not interact with each other as much. So just a little bit of review from a couple days ago. If we were to do this problem, what do I do? So let's break down. What am I trying to find? I'm trying to find the wavelength. So that's my objective. What am I given? I'm given the frequency is 97.1 megahertz, which means times 10 to the 6. And then hertz is 1 over second. So if we move that to a proper scientific notation, it'll be 9.71 times 10 to the 7. Because we took away one decimal place, it now kicks in another 0 in the exponent of the 10. So with that, we know we have to have an equation that has lambda and nu in it. So the only one that has those two as the main is C equal lambda nu. And remember, this is always a division problem. C, you should know, is the speed of light. So let's plug that in. We don't know wavelength, so we're going to darken that. That is our unknown. Time of frequency. And we can cancel the second, both sides and the bottom. That leaves us with wavelength, which is what we're trying to find, represented by the unit meter. Length, meter, makes sense. So we know we set it up correctly. I want the wavelength by itself, so I want to get rid of what's next to it. So to reverse multiplication, I do a division. And whenever you divide a number by itself, it cancels out. But the equal sign tells you that whatever you do on one side, you do to the other side. And so now just punch it out. I have left just the wavelength over here. I have the unit meter. And I grab my calculator and I go 3 double E or EXP on the Casio to the 8 divided by 9.71 double E or EXP on the Casio 7. And my calculator tells me roughly 3.09 meter. So the wave of most radio station, if it's an FM, will be from a couple meter to a few meter in length. AM, much longer. So, quick review also what did Heisenberg said. He said that it is not possible for you to say, hey, that guy's going fast right there, and also know exactly where he's going because you're so busy tracking how much he's changing compared to the background that you're not noticing the exact location of the background. Or you can say, hey, he's right there, and then you wouldn't be able to tell how fast he is moving because if your snapshot froze him in that moment, you know the position, but then he's not able to be described accurately of how fast his velocity is. So you cannot know both the position and velocity at the same time. So just a quick review. With that, hope you have a good day. Please do your quiz and Gizmo, get it done tonight. I would like to grade all the Gizmo tomorrow morning. Peace to you and have a good weekend with your family and loved one. Please remember, take care of yourself, take care of your loved ones.